Fukumoto and Sakuma, and I'll leave you to introduce the title of the talk. Welcome.
Sorry, this is a very long talk. Okay. Yeah. And the point is a unified view, topological invariants, and baroclinic fluids. And then this has two parts. Formal stability analysis of three-dimensional ideal gas flow with stratification. This is collaboration with Hirofumi Sakuma working on Japan Agency Marine Earth Science and Technology. So this beautiful picture was created by Earth Simulator in 2002. At the time, the best performance computer, and created by Sakuma's group. So this is Australia. So this is Eurasia, Africa. And you are looking at 100 meters below the sea level. And this is the integration of 50-year current. And you'll find abundance of bosses under the sea. So red one is propagating to eastward, and blue one is propagating to westward. So there are a lot to do for baroclinic bosses. Then I start with elementary knowledge. So static state is stable if density is lighter if you go upwards, and this is the condition for including compressible effect, and the condition if blunt biseral frequency is positive, and the incompressible limit is simply the lighter fluid is on the heavier one. But if you have shear flows, the shear flow can excite vertical motions, and then this potential barrier much stronger. So this is the condition for linear stability in two dimensions, and this is well known as Richardson number criterion. This number should be greater than a quarter. Then 30 years ago, Abravanel, Holm, Marsden, Latu extend this Richardson number criterion to 3D and nonlinears. And they estimated energy, and so Q is so-called potential vorticities. And they get sufficient condition for positive definiteness of quadratic form. But their treatment is it's too strong, because they treat velocity and potential vorticity are independent. But actually this is not independent, so this can be improved. Also, as examples, they treated not genuinely 3D, just weakly 3D. So this is almost 2D case, and they showed something mysterious result for positive definiteness. Richardson number should be greater than 1. So to our eyes, there are a lot to do, and progress is very little for over 30 years. And then today's main result is by using more Casimir's. Of course, they use Casimir's, but we use more Casimir's. We could derive energy estimate only in terms of independent variables. And Q is potential vorticities, and we are looking at not simply stratification, more general. dependence of density and entropy, then this is the potential vorticity. And as you know, Casimir invariant is any function of entropy and this potential vorticity integral. Okay. So now we consider a more general case, not ideal gas. Previous slide was for ideal gas, but this is very general Euler equations. Usually people, no, I make assumption of barotropic, but using local equilibrium of some dynamic conditions, this is more general equations. Then, so let's forget frame rotation. This is ATL's potential vorticity, and this is Casimir invariant. So before going to the energy estimate, the question is, what is this? Then this has two parts. And first, we consider how far is this Casimir from the helicity. Yes, many people have contributions. Casimir or helicity comes as an invariant associated with particle relevating symmetries, and here Asher has contributions. Also, there are beautiful talk by Professor Obalak. So people know in 3D, helicity is topological invariant, and 2D. For compressed case, this density, the function of vorticity is topological invariant. This is axisymmetric extension by Keith Moffat. So I thought this is very different. So I want to understand why different. So let's ask Neta. Then she said there is no distinction between 2D and 3D. So I was upset. Then I should 2D and 3D should be same. Then if you introduce this variable, f is any function of vorticity, function of x and y, but this is vector, and if you take curl, and then this quantity is a frozen field. And Neta says vector potential of frozen field and any other frozen field, this scalar product is if integrated. This is topological invariant. Then if you introduce this here, because this is frozen field, and just integration by parts, then except for the boundary term, this across helicity becomes two-dimensional Casimir. So let's repeat this for baroclinic case. And I owe much to the Larry Holmes formulations. And first, we start from Hamilton principle risk actions. And instead of freedom flow map phi, to practice particle releveling, the inverse map is more convenient. This is definition of inverse map. This is map and inverse. Then return original by taking a time derivative. You find velocity is written in terms of leveling. I think many of you have heard this from Larry Holmes' lecture. Then by changing this inverse map, velocity field and density is changed like this, and entropy is like this. The assumption is adiabatic. So this is the assumption. Sorry, I should say. Oh. Yeah. So assumption is conservation mass and adiabatic. Then the variation of action. This is Lagrangian densities. At the moment, you need not define the concrete form. So any function of velocity field and density and entropy. Then if you take variations, you obtain here the Euler-Poincare equations, and this is baroclinic effect. And this surface terms and boundary condition and initial conditions cancels these terms, and you end up with Euler-Poincare equations. This is correction by baroclinic effect. BI is defined by this, and if you introduce ordinary Lagrangian kinetic energy and internal energy and potential energies, this B is same as U, and T is coming from this. Okay, and for making realization of particle relabelings, it's easier to transform into material coordinates. And so project this vector potential to these directions, then previous equation becomes much simplified in this and corrected by baroclinic effect. Then by boundary conditions, you end up with Euler-Poincare equations written in terms of material coordinates. Now, let's use this identity. So, given the current position, current density and mass and entropies, let's change particle levels. So this is the conditions. Current state should be no change, but level changes. Then this gives constraint for generator, this, and also this is a new one. And you can easily check by these transformations, action no change. Then this identity is obtained, and if you assume Euler-Poincare equations, then this is left. So it's obvious this is conservation laws. Now take care about this constraint for baroclinic effect. So this is conservation. If you put this, and so this is constraint, and this conserved quantity can be written like this by introducing this way. Okay, so this is only conserved quantity, what nature says. So no distinction between 2D and 3D. So you think 2D Kashmir should be written like this form. This is cross helicity. This is a vector potential not for frozen field. This field, not frozen. And this is a frozen field. And this must satisfy this constraint. This constraint preserved in time. You can check. So to make that Kashmir, you can put this. Then you can prove this satisfies the desired conditions. Then you put this into here, and by taking partial integrations, you get this Kashmir invariant. So for baroclinic fluid, or the invariant associated with particle relabeling symmetry is a cross helicity. Just this should be not vector potential for frozen field. This is some corrections, and then I try to make examples close to helicity. while this, so this is Euler-Poincare equations, including Euler equations. Then this can be rewritten into this form. Then take curl. This is frozen field. So this and the vector potential is exactly in the same way as the helicity in barotropic fluid. So this is not the same class as this slide. This is just outside the class, but anyway, it's a topological invariant in the same sense as barotropic fluid. And I don't know this is new or not. Here, tau is just tricky. Tau is material derivative tau coincides with t. So you must integrate in some sense, in Lagrangian sense. Then this becomes helicity. Okay. How many minutes? Maybe almost 5 minutes. Yes. Then we use more Casimir than Abravanel and Holm and Mouth and Lattice, and to get an estimate of second energy to second order. Now we specify this is enthalpy, but for ideal gas, but include rotation. So potential vorticity is now this. So this is typical Casimir's. The energy is given by this, and first variation is easily calculated, and by inspections, so B is Bernoulli function. By inspection, if this vanishes, not by inspection, by some calculations, other terms also vanishes. So this is equilibrium conditions, and steady state is obtained from here, and we assume following: S and Q is not parallel. Then second order variations. This needs some calculations, but anyway, straightforward calculations leave this term, and so we want to cancel this term. In order to this, we introduce this vector satisfying this, and also by introducing another two Casimir, then we can kick out this, because this omega and B velocity is related. So we want to write all the quantity in the velocity and density and entropy. Then this final result, and we come up this. Yes. So Sakma did all the calculations, and I traced his calculations, and this result is simple, but something miracle happens. This is rather non-trivial. Yeah. And so positive definiteness condition is simply written like this, and so this is much less ambiguous than a previous result. And but it's not simple to extract information from here. So first specify this unidirectional flow, but not 2D, just 3D. Then this becomes reduce this form. M is Mach number. U star is connected with Coriolis parameters. So this is compressible case, and if you consider the incompressible limit, this reduces to this. And this is close to the Richardson number criterion greater than unity. It's the same one Abravanel obtained, not quotas. This is curvature effect. This is known to the is obtained by some other body, and so these are new terms. So this is Richardson number criterion and corrected by curvature, and something new. Theta is potential temperature. Q star is just logarithm of Q. So conclusion. This has two parts, and for baroclinic fluids, all the invariant associated with particle reverberating symmetry is cross helicity. This vector potential for the general Euler flow, and this another closing field. And other than this is also topological invariance. Tau is integration, Lagrange integration of temperatures. And we introduce another two Casimirs. Then we overcome previous results and to obtain less ambiguous second order variation energy. Thank you very much.
Thank you very much. Yes, please.
Maybe it's a question or a short comment.
Yeah.
So this algebra was for the first time made by Dickey in '65. Dickey, very shortly after the Arnold's pioneering work. And there appeared this dangerous term, which I believe is unavoidable. Then William Blumen here performed this analysis for a special class of perturbations, which allow to eliminate it. So for me it's a bit a miracle how, but of course it's necessary to look more into details. And my final very simple remark, on one of the first slides it is shown that the condition that the Richardson number is greater than 1/4, it's a necessary condition for stability. It's sufficient indeed condition, as the theorem of Miles-Howard tells us.
Thank you. I want to know this second one's contributions. Thank you.
Yes, please.
Thank you for a very clear talk. I just had one comment. The paper myself is quoted from 1995 was generalized later in 2008 by myself and Donald Lindenberg for cross helicity in MHD, but only barotropic MHD. Okay. So it's not exactly what you've done, but it's some resemblance.
Thank you.
Yes, please.
On your last slide, you have a sort of new helicity. Is there any interpretation of that in the topological sense? The very last, on the last slide.
So usually people use. Sorry. Oh, this is important.
The middle, yeah.
And this one. Yes. This one.
Yeah.
Yes. Yes, people use Bushnevsk approximations, and I don't try. But if this is reduced to Bushnevsk approximations, you can see something related. And so this is very difficult to calculate. But I think this is useful for the density interface or something like that. Then only contribution is localized. Yes. And this should be starting point. And this is what I want to know.
Thank you very much again, Yasuhide.